Good morning or afternoon or whatever time it is to everyone joining us today. We're excited to start our second week of summer program. Hopefully we have resolved issues that people were experiencing last week, but we are still looking at our email. So if there is an issue, we are going to handle it today. Today, our speaker is Vardaan Sahgal. He is with Wiser, and he's going to be talking about quantum and AI. He's our head of quantum solutions. And then we can also have a discussion of Q&A after his presentation. So I'm going to let Vardaan take it off.
Okay, perfect. Thanks a lot, Rachel. Good morning, good afternoon, good evening, everyone who's joining in from various places across the world. Happy Monday. I hope you have a great start to the week. And today we'll be talking about a very interesting topic of the integration of quantum and AI across a lot of different verticals, right? I'll just take a minute and start sharing my screen. But while I do that, the main focus of my today's talk and today's session would be that quantum and AI, we keep hearing about those terms, right? We also have the theme of our summer program this year as quantum plus AI. But the big question is this all hype? Or is there actually some practical, developments for here? Is there some kind of reality check to it as well? So maybe before I begin my today's session itself, and by the way, this entire session today would be very interactive. So try to have your Discord channels open and handy. If not, your Zoom also works. Just a thumbs up reaction or some kind of reaction over there works perfectly well too. But the first question for you today is, before I even begin my conversation today, is what do you think? Quantum and AI, two very different technologies often talked about together. Is this more of a hype, or is there some reality to it? And for those who are joining us today, for all the questions, whether you want to ask or whether you want to answer, the live chat channel on your Wiser Discord is where we'll be observing all the chats. So I see a lot of people already started typing. Let us wait for a quick few seconds and see what kind of responses we are receiving. Okay, while we're doing that, another quick question. Are you all able to see my video and my presentation? If yes, can I get a thumbs up on Zoom? So my presentations are visible and my video is also visible. Okay, perfect, great, beautiful. And we have started receiving some responses. Okay, so Surya mentions quantum and AI are two of the most disruptive technologies of our time. When they're combined, it has the potential to redefine computers. Okay, wordful, but I get your point. Yeah, two very disruptive technologies, but be very mindful. These are both independent technologies. So quantum can be really, really good in its own sense. AI is already pretty awesome in its own sense. The question is more that, are these two technologies even related together? Why do we often keep talking about quantum and AI, quantum plus AI? So the question is more about together. Is it more of a hype? Are we just, bringing two technologies together for the sake of it? Or is there some reality to it? Okay, I have another response from Ishan. Yes, there are realities. It can be used for solving various optimization problems. Sure, yeah. Let's see. I'll be talking a little bit about that in my today's talk. So I'll get back to that particular point. Ajay from India mentions AI decision-making can be improved by quantum. That's a pretty a bold statement. AI is pretty awesome today, right? As I like to call it. So it has already set a pretty high benchmarks on what is possible, and now stating that quantum can help AI improve its decision making. Yeah, let's see. Let's see. I won't comment immediately, but maybe after today's talk, every one of us would have a better understanding of what is possible, what is more of a hype today. I have a few more comments coming in. Quantum and AI can give us an edge over QNN, QML algorithms, solving complex problems at lower cost. Very interesting. Convergence of quantum and AI. Okay, very, very long answers. I'll try to read and go through them all. But I get your sense, right? Most of you are of the more optimistic folks today, which is great. I am also crazy optimistic in that sense. But maybe I switch the question over here a little bit. How many of you are more thinking of it as a hype? Maybe I can get some responses from them. Why do you think quantum and AI are just being pitched together just for the sake of bringing two technologies together? Why do you think this is just a hype cycle or bubble ready to be burst? Maybe we can get some more pragmatic answers up here as well. Okay, I love this response. Niklesh says that AI is getting added to everything nowadays. Sure, yeah, and for that matter, quantum too. And it is pretty obvious that both of them together is some kind of beautiful magic in place. So sure, yeah. I have another response. Quantum has a lot of development to be done in air crash and other things. It's still, a premature technology. It's still very nascent in its development stage. Very true. Correct. Okay, so we have both sides of the coin and both kind of participants here in the audience today, right? So wonderful. So my point was exactly this, right? We see a lot of quantum and AI being put together in variety of different aspects as well, right? And if you start thinking of it from a purely hype perspective, you will obviously see gaps in between both the technology. Quantum is still very early stage. AI has been around for many, many years now. It's already mature. And often, if you ask a purely AI person, they might not even know about quantum, right? So why are we suddenly putting both these technologies together? And the purpose of my presentation and my session today is exactly this. I want to give a little bit more on a practical understanding of what these two technologies mean if we want to combine both of them together. What are some real areas of research and development that all of you can start working on? And what part of it is still very, very hyped? Right. So we'll talk about all of these important questions today, try answering all of them. And by the end of the session, my expectation will be that all of you will have at least an improved understanding of what makes sense today, what makes sense tomorrow, and what is purely for the purpose of, social media buzz and hype and just making, a more easily understandable technology. So with that, let's get started. And during the entire presentation, right, during my entire session, if you do have any questions, please feel free to put the questions on Discord. I have been monitoring Discord on my side over here. If there's anything, I'd be happy to interrupt and respond to your queries real time. So before getting started, a little bit about Wiser. So I work as a quantum solutions head at Wiser. That is the Washington Institute for STEM Entrepreneurship and Research. We are a global organization, but we are currently headquartered in DC, in the US. In our few years of research and development, we have done quite a few good things, and I like to very quickly highlight that. We have had 3 amazing startups spin off from our research teams in quantum communication, in quantum computing, and quantum sensing, respectively. We today have more than 50 quantum research fellows working with us. This in itself brings Wiser to one of the top quantum computing organizations in the world, dedicated to pure quantum researchers out there. We have had more than 20 successful industry pilots, and these are like fully fledged industry projects that we have in a part, right? So industry scale deployment and development in R&D for quantum native and quantum specific applications. And finally, we have been attached with been able to work with more than 85 plus partners. And these partners go across quantum software providers, quantum hardware providers, the pure quantum companies, non-quantum companies, national labs, research institutes, universities. So we really want to work with anyone and everyone out there. And due to this entire ecosystem that we have been able to build for the past many years, we today stand as one of the 4 members of the designated Quantum Tech Hub in the US. That is the the Elevate Quantum Colorado Quantum Hub. It is one of the largest regional consortiums in America, and we are very proud of the work that we do. We are a nonprofit at hand, so it's really a lot of effort that goes behind the scenes and amazing team that work day in, day out to make all of this possible. And I already see quite a few questions coming in on how you might be able to join Wiser. The best answer to that would be to try and find areas where you could be of good collaboration to Wiser by looking at our website, right? So go to thewiser.org and browse of all the different initiatives that we are involved in. So you work across 3 broad pillars. The first one is education and training. That is where the summer programs comes in. The second one is research. That is where this particular slide kind of gives you a high level overview. And the third one is startups. Again, quick summary over there. So if you are interested in being a part of any one of these as a researcher, as a volunteer in the education space, in any XYZ area, the best place to start is our website. And once you have identified clear, understanding of where is best niche where you would be able to contribute, shoot us an email, right? There are also application forms open. So we do have a few open positions at the moment, so you can apply over there as well. But if you don't understand anything, or if you just want to talk and get a better idea, just shoot us an email, right? We are a small team, so your emails might be a little delayed in responding. I hope you understand that, but otherwise we'd we really love to, hear from you. So with quick background, right, I'd like to take a step back and discuss a little bit more about why do we need quantum, or for that matter, why do we even need AI, right? It often falls back to Moore's law. So any one of you is aware of Moore's law? Can I get a quick thumbs up on Zoom if anyone of you is aware of Moore's law? Have they heard of it? Maybe they understand that. And if someone would be kind enough to put a brief description of what Moore's law means, what do you understand by that in the Discord chat? Maybe some of the other participants can get a quick overview of that. I see several people are typing. That's encouraging. Let's wait for a few seconds. Okay, yeah. So we do have a few definitions. When someone shared almost a perfect description, so that the Moore's law is more of, it's not a law per se. It's more of a trend that has been observed over many years. It's now become more of a universally accepted fact. It basically says that every 2 years the costs drop and the size of the the classical computing chips, the silicon chips, keeps on decreasing. And because of that, the computing power keeps on increasing. But that has been, it has been almost true since a long period of time, but gradually that is now getting stagnated. So if you look at the graph on the right-hand screen, you can see that the size and the performance of these computing systems have been, linearly increasing over a certain period of years. But after a certain time, after like roughly 10 years back, that increase in the performance is gradually slowed down. Now, does that mean that the computers are no longer getting better? No, the computers are still getting better. But the rate at which we are getting better, faster, more efficient computing power in its raw sense is getting slowed. And that is purely due to the fact that silicon chips cannot get any smaller, right? You can go to a certain limit, but beyond that, there's a scary paradigm of stagnation. You just can't get smaller than a certain point. And that is what we are approaching. Because of that, the efficiency and the speed at which computers are being developed is decelerating. And as a result of that, we need better, stronger, more powerful computers because we no longer can increase the computing power of classical computers. We need something new, something more powerful, right? And that is where there is a need for AI, or for that matter, even quantum computing. Who knows what will be used in the next many years to continue, but we definitely need something more powerful, right? Another point over here is that energy demand. So we also need more powerful, more efficient and better computers because the power consumption of these HPCs, and HPC, I just take it as a reference point, right? High performance computers across the world, these are the most energy consuming power stations out there. They have been increasingly consuming more and more power in the recent few years. So if you look at the graph on the right-hand side, that would give you a pretty a clear picture that after the 2020 kind of period, we saw a huge increase in the consumption of these HPCs, right? In the consumption of energy through these data centers, through these high-performance computers, supercomputers, and stuff like that. And because of that, we are reaching a stage where water is scarce, energy is scarce, and we need more efficient systems. So can we consider quantum as an alternative to that? If not, can we find ways where AI can be, made more efficient, or classical systems can be more efficient, so that we can, kind of overcome the current difficulties that we're facing, right? So these two in itself kind of make up the two very strong criteria of why we need something new. And when I say something new, one part of it is definitely quantum, but it's not just quantum, right? We are starting with a blank page over here. If we can find any kind of new computing paradigm that is able to help us solve these two problems, we are up for it, right? So we are not just using quantum for the sake of using quantum. We genuinely see that quantum computing can make some good differences over here. Maybe a quick question over here. Maybe this is not that obvious to the participants over here. So I just wanted to have a quick check with all of you over here. The graph on the right-hand side, we do see a kind of exponential increase in the power that has been consumed by these supercomputers, by these HPCs in the recent few years. Any idea why is that so? Why is there a sudden increase in the power consumption? Again, the answers on the live chat on Discord. So let's see. Okay, first response already there. Bint Munir mentions due to AI. Okay, fair enough. We all saw the ChatGPT moment in front of our eyes. We are one of those generations which actually got to see that happen, right? So sure, more GPU usage, more usage of AI, data centers, more data servers. Yes, 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 and yes. Okay, so that is true. Having said that, I would add another item over here, right? So AI, we all understand that, yes, in the recent few years, use of AI has been way more than anything that was precedented before, right? And that is a huge, huge factor in this increasing quantum, increasing classical computer usage, increase in the energy consumption of these data centers. Having said that, there's another fun, technical point and statistical thing you would like to look at. And that is where I'd like to move to the next slide. And this is a quick, stat that we pulled from a NERSC LBNL supercomputer. That's the Lawrence Berkeley National Lab in the US, one of the biggest supercomputers out there. So this is the data collected in 2024. And if you see the total volume of problems that are being run on the supercomputer these days, majority of them are quantum related workflows. And that is very interesting to know, right? So I'm not talking about quantum computing to be specific over here, right? I am just saying quantum, and that includes quantum chemistry, that includes multiphysics, that includes DFT theory, that includes quantum chromodynamics, that also includes quantum circuit simulations, that also includes anything to do with physics, chemistry, math, with somehow relation to quantum theory in itself. And you'll see a lot of these have a clear role for quantum, and that is very interesting as well. So if you look at the right-hand side graph over there, the very cute quantum symbol over here represents some of the problems which are directly related to quantum in some way or the other, right? And you'll see a major portion of all of these problems are, in fact, quantum. So there are actually two reasons why the demand for energy has been increasing so violently in these HPCs, in these supercomputers in the recent past years. AI, no doubt about that. That's 100% true. With the increase in the amount of data that we are consuming, data centers, data servers, all of that combined does contribute a majority of the share in the energy consumption that we're having in these HPCs and data centers. But having said that, parallelly, we also have a very, very, encouraging contributions coming in from a quantum workload. And you can see that very significantly from this data extracted from Lawrence Berkeley Lateral Lab, right? And the best thing I like about this is that just today, and in fact, this is actually 2 years back. Today, these kind of simulations, these kind of workflows are even increasing. And now the question is twofold. Number one, can we find smarter, clever, more efficient ways of doing all these simulations, all these calculations? Do we still need classical computers for doing quantum calculations? Or can we start exploring quantum computers to solve all these problems? Because if you see, these all problems are quantum inherent in nature, right? As this particular symbol tells us, right? Quantum chemistry, DFT, scalable solvers, fusion, lattice, QCD, all of these things. Can we try and move these away from classical simulators and do them on quantum computers, right? That's a very valid question to be asked. Similarly, can we have quantum computers as an alternative to all the solutions that we have been, like crazy running on AI and data servers and classical machines? Can we use some part of quantum computers to help share the load? And the idea is the same. The two questions that we again and again ask. Number one, how can we have better quantum computers or just better computers because of the Moore's law decelerating in the few years, it's stagnating, so we definitely need something new. And the second is the energy crisis is just too dominant today to be ignored, right? We just cannot go away with this fact. We need to find something new, something better. So the idea is that quantum provides one very viable alternative to start thinking about these lines. So with that kind of background set, I would like to dive into two broad domains going forward. And the first one would be, using quantum for AI. So AI is there, right? It's not going anywhere. We have already had that breakthrough moment. AI would be integrated into most work streams moving forward. The question is, can we use quantum for better, faster, more efficient tasks that are already being run on AI with the core purpose of getting results either faster or with more efficiency? And why do we need that? Well, because to get better results, obviously, but also because if we can more, smartly use these resources, maybe we are also able to cut down on the resources that are utilized while processing data. Maybe we can cut down on the energy utilization while doing all of this. So the first purpose is quantum for AI. We are using quantum resources for improving AI processes. And the second one is the flip side, right? The other way around. Can we use AI for quantum? And this is more interesting, especially from people who are coming in from a non-quantum stack, people who are coming in from any other area, but just not quantum. So this is a very interesting domain for them to start getting their hands dirty, because quantum is still very new and it will, require any and all help that it can get. So if AI is good enough to help in even one small factor to improve the quantum technology landscape out there, we will very, very gladly accept that, right? So the second vertical is more about AI for quantum. And by the end of this conversation today, my goal would be to kind of help you realize that these are not independent technologies. In a way, yes, they are all independent. They all work very separately, but these need not remain siloed for the remainder of their lifespan, right? We need to find ways where we can start integrating these three technologies. We need to find ways where AI run on GPUs and classical computing routine, the core workflow of any kind of computation that we want to do today on classical CPUs, and our new and upcoming quantum hardwares are integrated in some way or the other, where at the end of the day, the problems that we are running or the questions that we are trying to get answers for are resolved in a much better fashion. We do not care whether quantum is being used or AI is being used or nothing is being used at all. The only thing that matters at the end of the day is that we can get some kind of advantage from all of these processes all combined together moving forward. So with that kind of a landscape, right, I'll dive into both these technologies one by one. And I'll try to pause in between to see if there are any questions, but I'll kind of move through the process accordingly. So the first vertical that we'll be talking it is how can we use quantum computing for improving AI? And right after that, we'll be talking about how can AI be used for quantum. So let's get started. The first one, right? How can we use quantum for AI? And this particular slide just gives a very quick kind of a visualization of why we even need quantum for AI, right? We are not being forced by anyone. We need to find a very clear indication of if we need quantum at all, right? And when I say quantum for AI, it's basically quantum machine learning in its more trivial sense, right? So whenever I talk about quantum for AI, it's basically QML that I'm talking about. And why do we need QML? Well, because it's been theoretically proven that quantum processes, quantum algorithms, QML algorithms can help us map data, the complex, really, really hard data set into higher dimensions. And when we do that, it helps running these machine learning algorithms in a much more easier fashion, right? To give you an example, right? A very, very trivial example, this is not to scale. We have much more complex algorithms out there which are actually being deployed at an industrial scale, but this is only for your understanding purposes, right? Suppose we have a very complex data set, right? Which you can see on the first figure over here on the left-hand side. A lot of these data points, all of them random, all of them distributed, and these are not separable when you try to look at them from a single dimensional, low dimensional perspective, right? So if you map them onto a two-dimensional scale, this is what it looks like. And if I were to try doing some kind of binary classification between them, I cannot find a single line, to cross them. So let's say I suppose I have a horizontal line up there. The black and then the gray and the white dots still kind of come in both the paths. If I try to draw a vertical line, again, I cannot find a single line which differentiates into two binary components. And that was the whole purpose of having a binary classification over here. But if we try to map this entire data into some higher dimensionality, so instead of mapping into 2D scale, we try to map it on some kind of a system. I won't tell you what this is, right? This requires a little bit of jargon, so let's keep it to that. If you're aware, then that's cool. But this mapping is called as encoding and embedding data into quantum machines. We call this for timing. Let's consider this as some kind of feature map in dimensions. And the interesting thing is that as soon as we start doing this, we see some kind of clear separation. We can already start seeing between the white dots and the black dots, right? And if we start rotating these, we start doing some operations within this quantum feature map, we can actually find a plane which clearly cuts between the black dots and the white dots. And we have our binary classification done. Voila, right? It's not as simple as this all seems, or it's visualized over here, but at least it's the starting point to help you understand why we even need QML for that matter, or why are we even considering quantum processes for AI, right? This entire stuff has been proven theoretically. So Mathematically, there's no doubt we need it. But the next step is to start implementing on a practical scale. And that is where more complex data comes in and much more complex need for algorithms also comes in. And that is something which we'll probably discuss in the next few sessions and lectures throughout the summer program, right? But for now, let's take this as an example. So what does the usual routine of these quantum algorithms look like, or what does quantum machine learning look like over here? And maybe this particular graph can help you understand that better. So I'm assuming that most people over here are familiar with classical machine learning, AI, or some kind of understanding over there, right? If not, I'll just recommend you to do a little bit of self-study after the session and get some kind of classical machine learning understanding over there, because that would be useful for this remainder of the sessions for this program as well. But to at least get started, this comparison is a pretty decent one to help you understand. So in the first figure that you see on the left upper hand corner, you can see this very, very trivial flowchart of what a classical machine learning model might look like, right? We have some kind of data sets over here. It is being encoded and done using some kind of, over here it shows some kind of tensor networks over here, right? But we won't get into that. Some kind of classical computation. And by doing those set of computations, we get a classical prediction, whether something is correct or not correct. These kind of predictions might vary in different kind of, data sets, in different kind of problem statements. We can have classification problems, regression problems, time series prediction problems, any kind of machine learning problem in its own sense, right? But that's kind of a very clear architecture of what classical computing looks like. But my point was that we want to be able to map this entire classical data into higher dimensions. Remember the previous slide where we talked about the ability of quantum algorithms to map it into higher dimensions? That is what we'll be doing in the quantum computing regime, right? So we still have the classical data. We start with the same thing, but then we have an additional step called as encoding or embedding. And these are strategies which we use to use this classical data and somehow encode it into quantum data, right? And maybe quantum data is not the correct word to use over here. It's basically the same data embedded onto qubits, right? And that you could call it as quantum data if you want. But the idea is that we put all of this classical data onto your qubits. And that is done using some kind of encoding strategies. Once your data is on the qubits, then you're more than free to play around with it. And we use all sorts of gates and operations and different kind of algorithmic routines over here to kind of play around with it. That is called as quantum computation in its very core sense. Very similar to how you did classical computing, right? So in your classical machine learning algorithms as well, there are a variety of different algorithms that we use. Similarly, in the quantum computation part as well, we have a variety of different algorithms that we'll be using over here. And after that, we get some kind of output, similar to what we did in the classical end as well. After the algorithm, we need an output. One more step over here is that we need that quantum output to be translated into classical output, because we cannot understand what quantum output is. We need it in classical understanding. So there's another decoding step over here. And after that, we get the same kind of results. The idea is, back to the previous slide, this entire process is useful only with the mathematical understanding that this middle part will help us realize data in higher dimensions, and that may have some kind of advantage associated with it. It may completely fail as well, right? It may not work in all cases. So you need not try, just pushing quantum down the throat of certain problems just for the sake of it. So if there is a problem and that is working fairly decent, fairly competent on classical algorithms, that's good enough. If you want to try just for the sake of trying, for sure. But there would be very, very niche set of problems that are really, really difficult, intractable on classical dimensions. And that is where we would require the need for representing the same data in many, many more dimensions and solving that using quantum computing. So that's kind of the idea over here. Another question over here, which might be relevant, is that quantum for AI is quantum machine learning in its pure sense. There's one more thing where quantum for AI can be useful, and that is a variational quantum algorithm. And if you still this session, I am assuming that most of you must be familiar with VQAs, the variational quantum algorithms. But if you're not, a very quick overview of that. It's basically any kind of quantum algorithm which uses both quantum computers and classical computers. They distribute the most difficult tasks between them and then try and solve some kind of a problem. right? It could be an optimization problem. It could be a chemistry simulation problem. It could be some kind of a sampling problem. It could be some kind of a physical simulation problem. It could be a machine learning problem. It could be anything, right? So this is the kind of a very big umbrella between under which a lot of these algorithms sit. But the idea behind these algorithms in itself uses quantum for kind of accelerating AI processes, right? And the idea is that in these quantum computing algorithms, we have something called as an ANSAT, which is a parameterized quantum circuits, right? And these parameters in these quantum circuits need to be the most efficient ones, the most correct ones to get to the results the fastest. And how do we find these correct parameters? That's an open question. So what do we do is we use the help of classical computers and try and iterate it again and again until we find the most optimum parameters to run our algorithm with and get the outputs over there, right? This is a very, very high level overview, but I wanted to include this slide to help you understand that when we are talking about quantum for AI, it includes both sets of arguments. The first one being just quantum machine learning in itself, and the second one being traditional quantum algorithms as a huge umbrella within which all these algorithms sit, right? So the idea over here is that AI is really good, right? We don't want to touch something which is working really good. But at the same point, we do understand some kind of, clear areas where AI can be improved. One of them being energy utilization. We want to make these algorithms much more efficient. And a way to do that might be using quantum for AI. And that is where QML comes in, that is where VQAs comes, right? So that was the kind of big picture stuff on why and where quantum for AI can be utilized. So I'll take a quick breather over here and see if we have any questions on the chat. And after that, we'll bounce back to the second big topic, that is using AI for quantum, the flip side, the other way around, right? So let me go through questions. Oh my God, a lot of questions. Okay, I love this, but also apologies, I might not be able to go through all of them. So I'll pick and choose a few over here, right? Okay, so I had a question. Isn't density functional theory part of quantum chemistry? Yes, it is. It's just a different way of working, right? So it is. Okay, another question is, okay, this is a good one. So the question is, if quantum feature spaces can separate complex data more efficiently, will QML be able to lessen energy and training data costs for those contemporary AI systems? Or will the price of sustaining quantum technologies still surpass the quantum the computing advantage? Very, very good question. Unfortunately, I don't have a clear answer to this, but I'll still like to address the question. So just to make it clear for everyone, right? The questions is basically like, it was clearly stated that AI uses a lot of energy on today's data centers and today's HPCs, right? If we are able to improve those processes using quantum computers, will that help directly reduce the energy consumption? Or will using quantum computers just add to the energy factor over there, right? And for that to happen, we need a very, very clear apples to apples kind of comparisons between what kind of energy is being utilized on quantum computers, what kind of energy is being utilized on classical computers. That kind of comparison hasn't been done yet for obvious reasons, right? Because we haven't had the bandwidth to actually compute the same problem across both the systems parallelly and then kind of find out which system uses more energy. We could asynchronously try to get some kind of idea, but that would unfortunately be like comparing apples to oranges. We don't want to compare it on different problems. We don't want to compare it on different instances. We want to try and have those variables constant between the two systems as much as possible so we can get a clear idea. But this does bring up a very important point, and this is maybe an homework exercise. Some of the researchers over here in the audience can take it up as part of their maybe I don't know, like dissertation studies. Like maybe if you're doing your master's research or your PhD research, this could be a part of it, right? Just analyzing what kind of energy consumption is there on a quantum computer versus an AI routine run on an HPC, and have a very, very apples to apples kind of comparison over there. It cannot be asynchronous. So try to come up with some kind of answers. And maybe we are all 100% wrong. Maybe quantum is just not that mature today that it can help us reduce those energy utilization, right? And that if that is the case, we also need to optimize our quantum operations even further, right? So that is maybe a homework for the quantum hardware specialists out there. So we need that kind of report. And if people are joining from an industry perspective in this talk today, maybe this is a good exercise that you could take up from your organization level as well, right? This could be a very, very interesting report that could be, submitted as a white paper or some kind of publication out there that just compares what kind of energy is being utilized on the quantum computers, what kind of energy is being utilized on the data center. Is there any kind of comparison between them? So I really like that question. So shout out to whoever asked that in the chat. Okay, so we do have a few more questions. Okay, so there's another one. I like this question. Why do we need a classical optimizer in this kind of a weak way algorithm? Can't the quantum computer optimize the parameters in itself? The answer is yes. Quantum computers can do that, but we try to limit the operations run on quantum computer. So I don't remember it where, but I heard this example sometime back, right? Like if you have a Lamborghini, you won't use that to, travel to the nearby shop to buy vegetables for your house. You would rather keep the Lamborghini reserved for racetracks and for long drives on a highway or something like that, right? For your day-to-day travels within your neighborhood, you would either just walk or take a stroll on a bicycle or something, right? So you don't want to use something that is way too powerful for a very, very small task. And over here, we see quantum computers in a similar way. We don't want to use quantum computers just for optimization purposes for parameters. Classical computers are more than sufficient for doing that, right? So the question is, the answer to the question is yes, we can use that on quantum itself, but we also have classical for doing the same thing. I have another question. How does the choice of answer affect the performance of variational quantum algorithms, and how do researchers avoid issues like barren plateaus? Very, very quick question. I won't be covering this particular question in today's talk just for the sake of time, but this is a very important question. Barren plateaus, they do occur, and it's just unavoidable. We just need to find clever algorithms to fight our way through that. The choice of ansatz, yes, is a very, very important decision. So what kind of embedding techniques you want to use, what kind of ansatz you want to use, what kind of preparation while going into these kind of ansatz do we take into account? And this in itself is a very interesting research field. So maybe shoot us an email to whoever asked that question, and we'd love to take it up with you on a different chat. And maybe this entire topic will be discussed in way more detail in the upcoming few sessions in the program, right? So I like to keep it for future. It's just because of time constraints, right? I won't take it up today, but a very good question, and everyone should read more about ansatz preparation is very important. What kind of factors are considered while preparing such a thing? What kind of things we need to optimize? What kind of embedding strategies we want to use, and what in itself makes a good, efficient quantum algorithm? Okay. Okay, so the questions will not stop, right? I'll take a pause over here, and I'll move on to the next question. The next topic over here. And that would be the next broad category we want to consider in today's talk. That is the flip side around using AI for quantum. And this is very, very important for everyone who wants to start understanding quantum from a more classical perspective. Sorry, I missed one slide. Before that, a quick, primer on why quantum for AI might not work. This is kind of, very, very brief outlook on what all can go wrong if we are not careful about using quantum machine learning algorithms. And the idea is the same, right? We want data sets to be represented at a high dimensional quantum state. That is why we want to use quantum. That is why we want to use QML algorithms. But the problem is that data loading in itself is a huge bottleneck, right? We are still finding, more clever ways to make that work, but the embedding strategies are just not good enough today. We want more active participation from all the researchers over here to help us find a better alternative over here. The second and third points are purely on a hardware perspective. So the hardware is just not good enough, but at least I don't need to worry about it because I'm more on the software side. So my friends on the hardware side will worry about it, and they are working on it, right? So we have a lot of people around the world focusing more on the hardware side, working to make better, more efficient qubits, kind of understanding where we can fix the scalability and hardware limits. So all these different kind of qubit architecture, different kind of qubit modalities. So things are in progress. The fourth one ties back to the first point about data loading, lack of quantum RAM. The idea is that on the classical side, we have something called as a RAM, right? In all of our CPUs, there's a component called as a RAM, which makes instantaneous calculations, data reading possible. So it's like you have a data set, you pull data, you compute, you give the answer. You have more data coming in, you process more data, you get the results, and you put it out, and so on. It works on an instantaneous manner. In quantum, that does not exist yet. It's unfortunate. So the concept of RAM in itself is tracking in quantum computing. So we cannot make instantaneous decisions or any kind of computation in quantum computing just yet. Mathematically, sure. Theoretically, sure. But practically, not so much. So unless we have a real-time running quantum RAM, instantaneous decisions, instantaneous computations might not be possible just yet. And finally, obviously, we all understand that, right? Like just getting a theoretical proof out there, just getting a mathematical proof out there does not always guarantee an advantage. We need to get practical results out there as well. So this entire slide was just a primer, right? Like all the things that can go wrong if we are all working on that. Having said that, I am crazy optimistic, so I'm pretty confident that quantum for AI will work out, and all of you should feel the same. Okay, switching to the next topic, AI for quantum. Now, again, this is a very, very important set of conversations to follow over here, which demand that people who are coming in from a more classical perspective, people who have been working in the classical math, physics, chemistry, classical computational science for a long, long time, can help start contributing quantum. Because as I like to say, quantum is in a very early state at the moment. It's still underdeveloped. So we will like to get help from anyone who can help, right? So any place where you say AI can be helpful, we are welcoming you with open arms, right? So in quantum computing, the quantum stack for a quantum computer looks typically something like this. So at the very bottommost, the very first layer is the hardware layer, where you have all the qubits being architecture, where you have the hardware development for all those some kind of infrastructure being placed, design for its qubits itself, fabrication process, all of that. After that, you start designing your quantum algorithm itself. So that is where pre-processing tasks come into play. How do you formulate a classical algorithm into a quantum algorithm, right? That is where pre-processing comes into place. The third one is device control. That is where your quantum algorithm starts interacting with the quantum computer. And this could be in a variety of different ways, right? It could be in the form of microelectronic pulses. It could be in the form of photonic pulses. It could be something else, right? So depending on what kind of qubit are we interacting with, what kind of quantum computing modular hardware we are working with, these kind of device control and optimization works over there. It's very similar to just having an algorithm and making sure it talks correctly to your hardware sitting on the other side, right? So just that interaction itself is another layer. Now, once that interaction happens, the second step is getting the results. And more often than not, that results, those set of results that we are achieving are full of noise. Now, how do we resolve that noise? By using error correction mitigation techniques, right? So the error correction techniques comes into this stack, and error mitigation techniques come into the following stack. So the last two steps are more about dealing with errors in one way or the other, right? So this is kind of a very high-level overview of how the quantum stack stands today. And our idea is to somehow input AI in all of these stacks, in all of these different verticals of these stacks, to somehow help our quantum journey be as easy as possible, right? So next 3 or 4 slides, I'll be talking about each of these stacks in particular, each of these verticals in specific, and seeing where can AI help us out over here. Again, this entire conversation would be ideal for people who are already coming in from a classical background, that they can already start, getting their brain stems working and start seeing where can their free knowledge from this program be applied to quantum computing moving forward, right? So the first one is about hardware design and development. And when I say hardware design and development, I kind of put everything related to hardware in the same bucket. So this goes true for qubit fabrication. This goes true for qubit controls. It holds true for all the architecture and the hardware design that is kind of developed alongside it. So everything that has some kind of hardware associated with it, I put it into this bucket, right? And this was a very good kind of a machine learning of flowchart that I came across. The paper is linked at the bottom. So if you do want to explore or read more about this, you're more than welcome to read more in this Nature paper. But the idea is that at the first step, we train our models, right? We try to have some kind of a digital twin prepared over here, some kind of simulator prepared over here that behaves like a real quantum device, right? And we start simulating it in a way that a real quantum device would be simulated. Now we start, configuring different kind of variables over here. So we start optimizing the controls. Once we have these different kind of variables, different kind of parameters, different kind of, controls that we can play around with, we start optimizing this. And this is where the machine learning algorithm typically works, right? You try out something, it goes through an optimization function or some kind of a cost function, it optimizes the controls, it goes back into the model, it reiterates again. If it is correct, very good. If it is not very good, it reiterates again, and it goes on and on until we have some more optimized targets, right? But the important thing to understand over here is that this is not good enough. We need to have a third layer over here as well, where everything that we test on a simulator, on a simulated quantum device, also is worked on a real quantum device, right? So every kind of optimized parameter that we get from this machine learning algorithm also needs to be tested on a real working quantum hardware so that we can see some kind of developments in real time, right? Because we might be able to build the best digital twin, it's still a simulation at the end of the day. Unless we verify all of our results on a real quantum hardware, it's of no use to anyone. And once we start doing that, we also need to take into account many more factors that just are purely embedded in the hardware itself. So we need to take that into account. But the good thing over here is that all of these three processes, we now have a working model, right? And not just us, we have this entire process being implemented and tried out at many different places across the globe at various different companies. A lot of startups are also trying this out, and it presents a lot of good opportunities to anyone who wants to work on the hardware side, right? If you are coming from a classical AI perspective and you want to get your hands dirty on the hardware side, this might be an area you would want to start looking at, because optimizing these controls, optimizing the design and development of these different hardware devices in itself is a very, very important bottleneck in the entire quantum computing stack. If we can improve this, if we can fabricate better qubits, if we can have much better qubit designs developed, it would help us solve a lot of problems out there, right? So definitely something that we want to focus a lot of our energy on. Okay, so this was the first vertical in the quantum stack, right? Moving on to the second one over here. So once we have the hardware prepared, right? The second big thing is the pre-processing done, which is basically getting your software ready. So step one, get your hardware ready. Step two, get your software ready. And by software, I basically mean get your most optimal, most clever, most most efficient quantum algorithm out there, which can actually run on that hardware you prepared in step one. And to get that algorithm ready, there has been a lot of effort. And this is something I personally have been involved in a lot as well, because algorithms are just an amazing tool to talk with the computers. So we need to find the most clever and most efficient ways of running these algorithms in the noisy computers that we have today. And to help us with that task, we will like to use AI in every form, right? So one kind of small example has been represented in the flowchart below, but this is just one example, right? If you can find better ways of using AI to generate more optimized algorithms, we would all use that. In fact, I have a pretty strong feeling that this is already into production state from a lot of quantum software providers. A lot of people now have this kind of AI sequences embedded in their routines, right? No one wants to miss out on something. So if we are designing an algorithm, we would always use some kind of auto transpiler to kind of pull it down to the most efficient formation of gates, more efficient formation of operators to make the best use of our quantum hardware resources. It's just there, right? The question is, how do we make that more efficient, right? And that is for you to figure out. We need to find more and more better AI models that understand how we want to design our circuits, find better ways to design our circuits, and in a way, help us generate the most optimized quantum circuits out there, right? This is also maybe an opportunity for you all to start thinking about taking it to production stage, right? So I'm not sure how many of you are thinking, about taking your quantum projects to a startup kind of environment, but this is something which a lot of people would actually pay money for, right? So if you can have a plug-and-play solution, which I have an algorithm, you have some kind of software which just transpiles your algorithm, optimizes it to the best mode for a certain hardware, I would happily pay you money for that, right? So this is also an option for all of you to start thinking about where can you help develop models that can help optimize and get us the most, beautiful circuits out there, which are more convenient to run on quantum hardware resources. Right? So step one was hardware. Step two was quantum algorithms. It's basically done, right? But the most important thing now comes is how can we now create an environment where these algorithms are talking in the most efficient manner with the hardwares out there, right? And this is where AI for quantum device control and optimization comes into the picture. And this is basically your algorithms talking to the hardware and everything that comes in between, right? So this could be in terms of control electronics. This could be in terms of fine-tuning your qubits. It could be in terms of characterization of the qubits and the control functionalities, everything around that, right? And if we can find an AI solution to try and do that, it would be amazing. And sorry, I should have corrected my statement. It is no longer a fact of if, it is already in production. So very recently, a few weeks back or maybe a month back, NVIDIA launched this, right? This is no longer a theoretical concept. NVIDIA launched an Ising model, which is the first open AI model, as they claimed, to work on exactly this. And you'll have a few speakers from NVIDIA also coming in the summer program. We specifically invited them to talk about it, right? So this is a very, a kind of a golden opportunity for all of you to start thinking about this as well. Because you are not the only ones who are thinking about it. Everyone has started to think about this. The question is, how easily can you build something that is working over here, get it to production stage, and go to market, right? So if you have some ideas over here, we would love to work with you. I'd love to see how we can, accelerate this entire process, because a lot of complexities out there. Algorithms don't, work with the hardware as easy as it sounds. There's a lot of complexities around there. And if you can understand those complexities, find a way to optimize those entire control stack in itself, again, people will happily pay you money to get better results, right? So again, a very interesting opportunity for research for everyone who's interested in working kind of the middle layer between software and hardware out there. And maybe one last point I'd like to touch upon is error correction. So the point is that regardless of how beautiful our algorithms are, regardless of how perfect our qubits are fabricated, right? At the end of the day, quantum systems are just inherently very, very noisy. And today we don't have that good quantum error correction algorithms to get us good results. No, don't get me wrong. We have some state-of-the-art QAC algorithms out there, right? We have surface codes, we have topological quantum error correction codes, and a lot more stuff going out there. But if we can use AI to help us out there, we won't say no. We will, again, happily accept help from AI over here as well. So the idea is that we kind of train our transformer models with the kind of errors that we are seeing on these qubits and the position of our qubit. Once all of that has been put onto a transformer model, it helps us kind of predict what kind of errors might be there, right? And once we get a pattern of like, okay, these are the kind of errors that we are exhibiting, we can transfer to other code instances as well and already get an understanding of, okay, this is all that can go wrong. Now, why is this important? Because if we can understand what kind of errors are there, we can also prepare much better correction strategies to avoid those errors, right? So it's like if you know already something is going to go wrong, you can have some kind of, preventive strategies built into place to avoid that from happening. The problem today is that we just don't know, right? Errors will take place, but where and how and what these errors will be, it kind of depends on the noise. And we don't have the most efficient way of modeling the noise itself. So if we can use AI for predicting the errors on these qubits, it can help us a lot in identifying new areas of improvement on these error correction things. So with this, I'll kind of start wrapping up the discussion over here, right? So we talked about quantum for AI. The next was we talked about AI for quantum. And all this in itself is part of what we do at Pfizer and much more as well. We are very proud to work with a lot of partners across the globe in these kind of cutting edge research areas, including some of the best national labs, Naval Nuclear Lab, for instance. Some of you might not be available. Yeah, they might not be aware of what NNL does, but it is one of the most unique labs in the history of the country. They have been around for hundreds of years, and in their hundreds of years, they were the first ones to develop nuclear reactors, the first ones to develop nuclear aircraft carriers, a lot of firsts to their name. And while doing that kind of cutting edge research, right, they have had not one instance of failure. They have had 100% success rate over their hundreds of years of research and development, which is required. Because if you're working on something that is nuclear fusion related, you have to be 100% accurate. The offset to that is just, major calamities. You cannot afford that. With that kind of efficiency, we love to work with partners like that who also help us push to the limits of what we want to present and what kind of research we want to undertake. We also work with startups, the Classic, BQP, Pramatra, amazing startups that we have had the option to work with. We work with quantum players like Xanadu and IBM and many others. We work with some of the biggest institutions in the world like Eon and Vanguard and research centers like Fraunhofer and many more, right? So we work today with more than 85 plus partners. And while working on all of that, we make it a point that 3 core pillars of our research are followed. Number 1, application. Anything that we want to do needs to have a real world impact to it. Number 2, we want to make it utility scale. any kind of experiments that we're doing today, we want to make sure that these are not just toy experiments. We push it to the most, limit and make it 100 qubit plus experiments so that everyone can see some kind of, reality and some kind of expectations coming out of it. We want to understand what is really possible today and what is also possible in the next 5 years, what is also possible in the next 10 years to come. So scalability is a very important factor of anything that we do. And the final is benchmarking. We want to understand that any solution that we develop today on the quantum side, it's benchmarked and it's compared against the state of the art on the classical side, because only that kind of true analysis will help us understand where are we currently lacking and where are we currently lacking and where we can improve moving forward, right? One very quick example, which I'd like to highlight today, is one of the projects and one of the research areas that we did with the Fraunhofer Institute. And I'm highlighting this because this is very relevant to the theme of discussion today, right? Quantum for AI. And over here, we utilize quantum machine learning for anomaly detection. So this is basically identifying defects, identifying anomalies, identifying outliers from a huge data pattern. So think of it as like, we are doing a lot of financial transactions, and there's maybe one or two anomalies in between that, and those are outliers, right? Those are fraudulent financial transactions. How do credit companies, how do banks and different kind of financial institutes identify these anomalies, identify these fraud, transactions using something called as anomaly detection, right? Similarly, there are manufacturing units. A lot of things are manufactured day in, day out, and we need to have a control over a quality assurance control over anything that is manufactured. So any kind of defect in the manufacturing of different kind of products needs to be understood. So maybe some kind of sensor data, right, which just captures an image of whatever has been developed, puts it onto an algorithm, and it runs it through whether there are cracks in that particular material, right? Again, some kind of optimization for those kind of algorithms would be helpful. And we started using quantum machine learning for these kind of anomaly detection problems. And to our standard, not did we only run these to the best of our abilities, we also did a very thorough benchmarking study. We validated it on 3 data sets, 1 synthetic and 2 real data sets. We had not 1, not 2, but up to 6 quantum encoding strategies compared and studies very rigorously. And we also created a roadmap for reproducibility. Right? The entire work that we did with Fraunhofer has been put out to open. In fact, we also had a webinar on this just last week. And the idea is again the same, right? We want to make sure that any kind of research that we're doing today is made available to everyone and supports everyone to start working on it. So whether you're coming from an academic background or from a research perspective or from an industrial background, we want to make sure that anything that we're doing at Wiser is maintained to those kind of high standards, and you can implement them as soon as possible and contribute back to science. So if you are available, this is the press release, all of the data, all of the data sets that we use, all the algorithms that we use are also put on GitHub. The paper is also out on arXiv. So if anyone is interested, you're more than welcome to read more about it and take it from there. And with that, I'd like to wrap up for today. Thank you, everyone. I had a pleasure of talking to all of you today. We had an amazing session in the chat as well. And this is a quick snapshot of our amazing team behind the scenes working on some of the most cutting edge research over there. So when we talk about research, it often looks like we are all, nerdy scientists sitting on desks and just, taking our brains out all one at a time. But no, we are a fun group, right? So we love to take some time out for fun as well. So if you are ever, get a chance to meet us, do come say hi at our next quantum conference, wherever they are at in the US or globally as well. We'd love to connect with all of you. Please do not hesitate to reach out to the Wiser team. We are a small team, but at the same time, we want to connect with all of you over here today, right? So whether it's connecting with us on LinkedIn or shooting us an email, please do not hesitate at any point of time. I am sure you might have a lot of questions moving forward. So we'll take maybe the next 5-10 minutes or so to go through some questions. But as I scroll through that, just a quick reminder, if you do have any questions, if you do want to discuss anything, share your thoughts, comments, the live questions chat on the Discord is the best way to go. So with that, let me go to Discord and we'll quickly go to some questions. There are a lot of questions. Okay, so give me just a quick second. I'll just keep scrolling and try to pick it up from where I left off. Okay, so I have an interesting question from the US. Could AI predict fidelity collapse, congestion, or routing failures in a quantum network and use a variational quantum circuit to improve decision making? At a high level, I would say yes. This is indeed a very interesting problem, and I would encourage for you to start thinking a little bit more about this, of what are some clever areas where you could start implementing them. So high level, absolutely. Now, how do you do it practically? That's a question you will have to try it on your own. Okay, another question is, does quantum machine learning demonstrate a clear advantage over classical machine learning on any real world task, or is it still mostly theoretical? Good question. I would expand the question a little bit more, and this stands for any kind of quantum computing algorithm out there. We do not have a quantum advantage on a practical sense achieved just yet. Everything is just theoretical at the moment. Anyone who's claiming a quantum advantage, we will find a classical algorithm to outperform it, right? So that is the state today. Classical has been around for hundreds of years, right? You need to digest that. If there is a new computing paradigm that is coming up, quantum computing as we call it, it needs to compete with hundreds of years of research and development and engineering that has gone into it, right? But the good news is that we've already started competing against it, and competition is not always about winning. In a way, it is about winning, but it's always at least to making sure you leave a mark, right? You get to some results which are at least significantly good to at least come into the same picture as classical results, and that is what we are currently already observing, right? In the years to come, the hardware will develop. There's no doubt about that, right? The hardware will tremendously improve in the next few years. And parallelly, I do hope that the algorithms will also improve, right? And that's on quantum researchers like me and an amazing team that we have at Riser over here. So as both software and hardware components of quantum computing improve, I do believe that quantum advantage is just around the corner. It's as the chief of IBM just shared at the last conference, it's not a question about if, it's more of a statement of when. So we are already at the stage where we do see it happening. It's only a question of when will it happen, right? Is it 2 years? Is it 5 years? Is it 10 years, right? So this will definitely happen, just not yet. Okay, I have another question. Quantum RAM doesn't exist, but the science behind quantum RAM would be different among these various qubit types as well. Correct? Yes. So as does with most control electronics out there, if we do have that kind of a theoretical concept built, it would probably be very, very specific to what kind of qubit modalities we are dealing with. So yeah, how is QML related to quantum inspired algorithms? Are they overlapping? Are they distinct? Where does it fit in software development lifecycle? Okay, so I'll take a step back, right? So quantum machine learning is in itself a type of algorithm. And we have different types of algorithms. There are quantum optimization algorithms, there are quantum chemistry simulation algorithms, there are quantum sampling algorithms, there are quantum physical simulations algorithms, right? So there are different categories depending on the use case that we are targeting. And all of these algorithms together can be, caught up in a bucket, a different kind of bucket, depending on what kind of filter are we using over here, right? So either the algorithm runs purely on a quantum computer. In that case, we call it a pure quantum algorithm. If that entire algorithm runs on partially quantum computer, partially classical computer, in that way, we call them as hybrid or the variational quantum algorithm, right? And maybe that entire set of algorithm runs purely on a classical system, which is a classical algorithm in its sense, but it got some kind of inspiration, some kind of ideation, some kind of theoretical concept borrowed from a quantum information theory. In that case, we start calling it as a quantum inspired algorithm, right? So either which ways, all three of them are equally important, at least today. Maybe in the future, pure quantum algorithms would be the way to go. But today, I would give equal significance to all three categories, because anyway, we are doing software development, right? So it hardly matters which way we are targeting, which kind of compute resources we are using at the end of the day. If you're making some kind of advantage, it is helpful to us. So yeah. Can a GPT model actually discover a better quantum circuit than one designed by a human researcher? I would say yes. So just to clarify that question, right? If we are saying, can a GPT model just randomly come up with a better quantum algorithm? The answer is probably no, right? Because the data set that we are working in is limited, right? GPT models will run on the already existing knowledge. So it would probably return with the same kind of algorithms that we are all already familiar with, right? But if we are saying that we already have an algorithm that is developed, we find some kind of a custom GPT model or just a custom machine learning model that runs on that algorithm with customized parameters to fine tune and iterate and optimize. Can, in that case, we find a more optimized version of that algorithm? The answer is definitely yes. That is what machine learning is for, training and finding better answers. So the answer to that question would be yes. Okay, I have a good question over here. How can we ensure that the next generation of sovereign quantum enhanced AI systems is designed with universal accessibility? Okay, a tough question, but a very important one. So I would encourage all of you to start thinking about these lines as well. It's a nice period to be alive in, that we are seeing all of these new technologies come in. But at the same time, we want to make sure that any kind of new and upcoming technology that we are working on is also accessible across borders, right? We don't want to restrict any kind of knowledge to a certain niche corner of the world and then have some kind of, sovereignty over it. So you want to make sure that everything is accessible to all. Only that way we can progress as humanity in its most core sense. And that requires a lot of information from a global perspective, right? I perhaps might not be the best person to comment on the different global policies and different global economic development consortiums out there, but I do want to emphasize the fact that, at least from WISE's perspective, we as a nonprofit do put a lot of emphasis on open science, right? Most of the work that we do has a mandate to be put out into research publications or put out at conferences or some way or the other made accessible back to all of you, right? Having said that, there are instances where you do work with corporates as well, where IP protection is important because they also, at the end of the day, want to make some kind of profit from any kind of IP that they are developing. So it's kind of a trade-off between both. You cannot win one way or the other. You have to make an honest trade-off between the two strategies, and that is an important aspect that all of you should also start thinking about. What makes more sense as an open science perspective and what should be IP protected at different verticals of the quantum stack itself. Okay, questions won't stop. So maybe one last question over here. Can quantum computers be much more efficient in classical computers in sampling type of algorithms? The answer is yes and no. So yes, in the sense, theoretically, yes. I do see a lot of potential in quantum sampling algorithms just because quantum is probabilistic. That's probably not a best argument out there, but yeah, we do have a lot of arguments in place that theoretically prove that yes, different kind of sampling algorithms, whether that is Gaussian sampling or some kind of bosonic codes out there, maybe Monte Carlo approaches out there with some kind of quantum inspired algorithms or some kind of purely quantum approaches out there, which can be better alternatives to classical sampling techniques. That said, it hasn't been proven practically yet. The advantage hasn't been there yet, just like any other quantum algorithm. So yes, in the sense that it is possible, no, in the sense that it is not ready today. I hope that answers your question. So I see we are already over the 1 hour period, right? It was an amazing session today. Thank you everyone again for being here. Such an amazing audience. Again, if you do have any other questions, please keep the Discord chat alive. I would encourage everyone to learn from each other as well, right? A lot of you come from very different experiences, very different backgrounds. So this would be a very interesting time for all of you to start collaborating with each other, right? Maybe someone has an interesting idea and you want to do research together. Try to find people who are with the same kind of, background or coming in with the same kind of motivation and start doing collaborative projects together. We would have challenges and projects as part of the summer program itself that would be announced a little later. So please be tuned for that as well. But otherwise, it was really fun talking here today and hope to see you all continue with the rest of the program itself. Thank you, everyone. And with that, hopefully we can close today's session today.
Thank you so much, Vardaan. Very interesting. It seems like everybody was really enjoying it and being engaged. We will have this posted by the end of the day for you to view on the LMS and on our YouTube. And again, we are addressing access issues. If you are still having that, please reach out to hello@thewiser.org and we will fix it for you. Wednesday, we're going to have Emily Tucker from Clemson University speaking to us. So we will see you then. Thank you so much.